Have you ever wondered how closely related physics and chemistry are? These two branches of science often overlap, especially when the system under study involves matter composed of electrons and nuclei. The fundamental laws that govern the behavior of matter apply to both chemistry and physics, as both are concerned with the interaction of matter and energy. The theory and various rules governing atoms, which are of paramount importance in chemistry, are ultimately explained by atomic and subatomic particle physics. This realm of physics is critically important for understanding how individual atoms are joined by covalent bonds to form molecules. It can also provide quantitative insight into ionic and covalent bonding processes by explicitly showing which molecules are energetically favorable to which others and the magnitudes of the energies involved. The physics of energy, specifically heat energy, is another crucial intersection between these two sciences. It tells chemists whether a particular reaction is energetically possible in the direction it is written, and gives the composition of the reaction system at equilibrium. One of the key tools in both physics and chemistry is spectroscopy, the study of the interaction between matter and electromagnetic radiation. Most of what we know about the structure of atoms and molecules comes from spectroscopic studies, a technique developed through the collaborative work of physicists and chemists. In essence, the study of matter and electricity in physics is fundamental towards the understanding of many concepts in chemistry, such as atomic structure, molecular structure, X-ray diffractions, radioactivity, periodic properties of elements, nature of valency, chemical bonds in molecules, crystal structure of solids, and more. So it's clear that the study of atoms, energy, and matter in physics is foundational to understanding many concepts in chemistry. The profound connection between these two sciences demonstrates that they are not isolated subjects, but rather interconnected fields that work together to unravel the mysteries of the universe. How does physics come into play in the realm of biology, you might ask? Well, let's dive right in and see how we can make sense of life using the principles of physics. Firstly, consider the human body. It's a marvelous piece of machinery, isn't it? And like any machine, it obeys the laws of physics. The mechanics of human motion, for instance, can be understood through Newton's laws of motion. When you throw a ball, run a race, or even just take a step forward, you're essentially performing a physics experiment. Now think about the process of metabolism. The food you eat is converted into energy your body can use. This is essentially a process of energy transformation, which is governed by the laws of thermodynamics, a branch of physics. Next, consider the circulatory system. The blood flowing through your vessels can be likened to a river flowing through a landscape. The principles of fluid dynamics, another branch of physics, can help us understand how blood flow is regulated and how it responds to various conditions. And what about our senses? How do we speak, hear, or see? The answer again lies in physics. The process of speaking and hearing involves the creation and reception of sound waves, a phenomenon explained by the physics of wave motion. And vision, it's all about light optics and how our eyes interpret electromagnetic radiation. But let's not forget about our animal friends. Newtonian mechanics can also explain their movements. Ever wonder why a cheetah can run so fast, or how a bird can fly? Physics can provide the answers. Stability and equilibrium are also vital in biology. A body is in stable equilibrium under gravity if its center of mass is directly over its base of support. This is why you fall when your center of gravity is displaced beyond your feet. The principles of physics, therefore, are instrumental in understanding biological systems and how life functions. So next time you marvel at the wonders of life, remember, it's all just physics at work. Moving on from life sciences, let's explore how physics underpins the study of Earth and the universe. In the realm of geology, physics is a cornerstone. It helps us understand seismic waves that ripple through the Earth during earthquakes. This knowledge is not only vital for predicting and mitigating the effects of such natural disasters, but it also allows us to probe the internal structure of our planet. By studying these waves, we can create a picture of the Earth's layers, from the crust we live upon to the molten core deep beneath our feet. Physics also plays a crucial role in understanding plate tectonics, the movement of the giant slabs that make up Earth's surface. These movements are responsible for earthquakes, volcanic activity, and even the creation of mountain ranges. Fundamentally, it's the heat energy from the Earth's core and the forces it generates that drive these tectonic movements, and physics helps us quantify and predict these processes. Then there's the Earth's magnetic field, a protective shield that deflects harmful solar radiation. This magnetic field is generated by the swirling motion of molten iron within Earth's outer core, and understanding this complex process requires a deep understanding of electromagnetism, a key pillar of physics. Shifting our gaze skyward, we find that physics is at the heart of astronomy. It explains the movement of celestial bodies, from the orbit of planets around the Sun to the expansion of the universe itself. This is all dictated by gravity, a fundamental force in physics. Furthermore, the behavior of light, another cornerstone of physics, allows us to observe and analyze distant stars and galaxies. The study of light, or optics, enables us to decipher the composition of celestial bodies and the nature of the universe itself. As we delve into the Earth beneath us and the cosmos above, physics continues to be our guiding light. How about a field that is rapidly evolving and transforming our world? Computer science. Physics plays a monumental role in the development of computer technology, with its principles permeating every layer of this fascinating field. Let's start with the heart of every computer, the semiconductor. The transistor, a crucial component of semiconductors, is a product of solid-state physics. By understanding how electrons move in a solid, scientists were able to invent devices that can control and amplify electronic signals, forming the foundation of modern computing. Electricity, a fundamental concept in physics, is the lifeblood of computers. The binary system, which forms the basis of all computer language, is essentially electrical pulses being switched on and off. The principles of electromagnetism govern how these pulses are generated, transmitted, and received. But the influence of physics doesn't stop at classical computing. As we push the boundaries of what is possible, we enter the realm of quantum computing. Quantum physics, with its mind-bending principles of superposition and entanglement, is the driving force behind this cutting-edge technology. Quantum computers have the potential to solve problems that are currently beyond the reach of traditional computers, transforming fields like cryptography, optimization, and materials science. Furthermore, the principles of thermodynamics, another branch of physics, are vital in designing and operating these machines. Computers generate heat, and managing this heat is essential for their operation and longevity. Thermodynamics helps us understand heat transfer and guides the design of cooling systems. In essence, the development of computer technology is deeply intertwined with our understanding of physics, from semiconductors to electricity, from quantum computing to thermodynamics. The principles of physics are the building blocks upon which the edifice of computer science is constructed. In the realm of technology and computation, physics remains a fundamental pillar. So, what does all this tell us about the role of physics in science? First, let's retrace our steps. We started with the intersection of physics and chemistry. We saw how physics, particularly atomic and subatomic particle physics, provides the bedrock for our understanding of matter and its interaction with energy. It gives us insight into how atoms bond to form molecules, how reactions occur, and even how we can use spectroscopy as a tool to understand the structure of atoms and molecules. So in essence, chemistry is deeply rooted in the principles of physics. Then we moved on to the role of physics in biology. Physics explains the mechanics of motion in living creatures, the energetics of metabolism, and even the fluid dynamics of blood flow. It's the key to understanding how we move, how we speak and hear, and how we see. So you see, without physics, we wouldn't understand the basic functions of life as we know it. We also delved into the role of physics in geology and astronomy. From understanding the movement and formation of planets to the behavior of galaxies, physics is indispensable. It's the key to unlocking the secrets of our Earth and the vast universe beyond. And finally, we looked at how physics intersects with computer science. Quantum physics, for instance, is at the heart of the development of quantum computers, which promise to revolutionize our technological landscape. So, what's the big picture here? Physics, it seems, is the backbone of all scientific study. It's fundamental to our understanding of the natural world, from the tiniest particles to the furthest reaches of the universe. And not only that, it's continually pushing the boundaries of what we know and what's possible in technology and innovation. From the tiniest atom to the vast reaches of space, physics is the common thread that binds all scientific study together.